Hi students, good morning. Today we are going to see some important topics because these are the basic for all the higher studies. So please listen the video carefully. First we are going to learn about filling of orbitals. What do you mean filling of orbitals? Filling of orbital in the sense how will you fill the electrons in the orbital? Okay. So for that we need to learn three rules to follow the instruction or to learn about filling of electron. Okay. So first filling of orbitals means electron we are going to fill in the orbital by using three rules. Already I told. First one is aufau principle. So what do you mean aufau principle? Aufau principle means what? See, the electron should fill from lowest energy to highest energy. What do you mean that? In the ground state, okay, so several orbitals are there, okay. Remember, I am talking about orbital in the sense subcells, okay. Yes, so in the subcells you may have many subcells, so which one having the least energy, from that you should start to fill the electrons, okay. So condition is in a ground state, okay. So in the ground state, from the ground state, from the lowest energy to highest energy, you have to fill the electron, okay. What's the definition for aufau principle? Electrons are filled in the increasing order of the orbitals, in the order of increasing energy level of orbitals. So from lowest energy to highest. Sir, how can I know which one is lowest energy, which one is highest energy? Just now in the last video we have studied what is that? What is the energy order of all the orbitals? Yes. So by using that n plus L rule, by using the n plus L rule, we have studied or we have drawn the sequence of order of energies, okay. So the orbital, according to their increasing order of orbital, we have learned in the previous video. By using that we can fill the electron from lowest energy to highest energy. Simply you can remember aufau principle means electron should fill from lowest to higher energy. You want to fill the electron from lowest to higher energy orbitals, okay. We have to follow the n plus L rule, okay. So for that you have to use certain diagram like structure. It's very easy also, right? Better you can see page number 52, 2.12. See, by increasing order, one is to lowest energy, one is to, we can fill this following this order, okay. Next, Pauli exclusive principle. Pauli's exclusion principle. What is Pauli's exclusive principle? How many quantum numbers are there? 4 quantum numbers are there. What are the 4 quantum numbers? Principal quantum number, azimuthal quantum number, spin quantum number, magnetic quantum number, okay. In an atom, any 2 electron or 2 electron cannot have same set value of all the 4 quantum numbers, okay. Just we will remember that symbols of all the quantum number. Principal quantum number called that S, azimuthal or subsidiary quantum number L, then magnetic quantum number, then spin quantum number. Here you make it M, magnetic quantum number, spin quantum number. Okay, so by using this, right, any two electron if you take, even it may have same energy. Okay, but any two electron in an atom may not have all these four quantum number as the same value. Okay, that is the Pauli's exclusive principle. Okay, sir, I couldn't understand. Okay, if you see the example, we can understand. Okay, for example, hydrogen. How many electrons are there? Only one electron. Yes. Okay. So, what is the principal quantum number for this nitrogen electron? 1, because first cell. Yes. What is the L value? 0. Then magnetic quantum number, M is 0, L is 0 means M also 0. What about spin? Plus 1 by 2. Okay. See, one set of values. Okay. Right. But hydrogen don't have any second electron. So, which have unique numbers. Yes. If you take for helium, helium having 2 electron. For first electron, which having same order of the hydrogen. Okay, N value is 1 because first cell, L value is 0 because S orbital, L value 0 means M value also 0. One is in the upward clockwise direction, which spins in the clockwise direction, we can say plus half. But the second atom of helium, N is equal to 1, L is equal to 0, M is equal to 0, but S equal to minus 1 by 2, right? So, what is the Pauli's exclusive principle? One atom or any two electron in an atom cannot have same value of 4 quantum numbers. Okay, see, it may have 3 same value, N, L, M. Okay, so all first 3 values are same, but what is the principle? All 4 quantum numbers cannot be the same. Okay, see, the last one is different. Okay, MS or S both are same. Spin quantum number plus of minus of. Okay, so simply we can say always exclusive principle, how one subcell can accommodate only 2 electron. One is in the clockwise direction, another one is in the anti-clockwise direction. Okay, so as per the statement, any 2 electron in an atom cannot have same set value of all 4 quantum number. But from that easily we can draw, or for understanding we can say in one orbital, one subcell, right, 2 electron only may occupy, even though the 2 may not have same spin, one in the clockwise, another one is in the anti-clockwise. Okay, right. Then we could write some values of all 4 quantum number for different. Okay, right. For example, first electron in the L cell. We are going to learn about L cell. Okay, so the first electron. So first electron in the sense N value is equal to KL. So always the N value becoming 2. So the second cell is made up of S orbital as well as P orbital. So S will have the L value 0. Then M value, what will happen? Magnetic value, L value 0 means M value also 0. Then spin value minus half. Then third electron, first electron, second electron, N value 2, L value, but it becoming plus half. Okay. Then S orbital over, then P orbital, N value 2 only, L value becoming 1 because the second L cell having both S as well as P orbital. So P orbital means L value is equal to 1. Then L value is 1 means what about the M value? M will have 3 values. Okay. You can remember, I hope. What are the 3 values? It may have minus 1, plus 1, 0. So first one by one we will tell. Minus 1. here also plus 1 by 2. Then next electron, fourth electron. So L value here also 1. Here also minus 1 plus 1. Then here also it may have plus half. Then here we have 0. Then it may have plus 1 by 2. The same way we can write other 3 electron. How? 2, 1 plus 1, 1 by 2. 2, 1 minus 1 minus 1 by 2. For the same set, you just remember only you have to make it minus half half. Right? So if you check all 8 electrons having different all 4 quantum numbers, no any 2 electron having same 4 quantum numbers. See, even we have written 1, 2, 3, 4, 5 electrons. All are having unique quantum numbers. Okay. So that's why I told you when I taught that quantum numbers, this is important to locate the electron in the orbitals. Okay. Next to that, Hunds rule. What do you mean Hunds rule? See, aufau rule told that we can fill the electron from lowest energy to highest energy. What about the degenerate orbitals? What do you mean degenerate orbitals? See, p orbital, if you take p subcell, what will happen? It may have 3 arrangement, orientation, px, py, pz. Okay. So, if you want to fill the electron in the p orbital, which one is the lowest energy? Which one is the highest energy? No, we already know that what is degenerate orbital, all are having equal energy. So first you have to fill all the one with singly filled orbital. After filling the degenerate all the orbital with one electron, we can pair up the electron. That means even though if you have 4 electron, right, you should fill first 1, 1, 1. All the degenerate orbital should fill with a single electron. After filling all the degenerate orbitals, we can start to pair up. Pair up means you can make it pair with opposite spin. Okay, this is called Hunds rule. Okay, so we can write for a carbon to understand Hunds rule. Carbon, what is atomic number? 6. So electronic configuration 1s2, 2s2, 2p2. Okay, right. So for 1s we can write 1, 2. For 2s 1, 2 because they are having lowest energy. Last, so p orbital means which having 3 orientations. Okay, so 3 box, px, py, pz. Totally 2 electron. So each orbital can occupy 2 electron. Shall we? No, that is wrong. You should not pair up here itself. First you have to fill the electron. Why? If you have one more, we can fill here. Not pairing. Okay, you should not pair the electron. So avoid the electron repulsion. The electron, 6th electron, 1, 2, 3, 4, 5, 6, 6th electron goes to the py arrangement, not to pairing with the px. Okay, right? So Hunds rule is used to tell all the degenerate orbitals should fill singly until all the orbitals are paired up. Okay, right. The last, we are going to study about electronic configuration. What do you mean electronic configuration? See, electron distribution in the orbitals only called electronic configuration. So we want to learn, we have to write. For that we need some simplified arrangement, that is only called electronic configuration, right? In particular atom, the electrons are present in several subcells. So how will you tell which is belongs to this cell, then the subcell? So all this makes confusion. To avoid that confusion, we can make it as a simplified formula for electron arrangement. So what is electronic configuration? The distribution of electron in the subcells, orbitals, only called the electronic configuration. Okay. Yes, we have to follow a rule NLX. Okay, what's the rule to write about the electronic configuration? NLX. What is N? Principal quantum number. What is L? Azimuthal quantum number. X is nothing but number of electrons. How many electrons are present in that orbital? We can write in the place of X. Okay. Shall we write for hydrogen? Yes. Hydrogen. Only one electron. Okay. What's the N value? 1. L value 0. L value 0 means S subcell. L value 1 means P. L value 2 means D. L value 3 means F. So L value for hydrogen 0. 0 means S orbital. So here you should not write L. The L value you have to write. Okay. X 1 electron. So 1s1 is the electronic configuration of hydrogen. Okay. Right. The same way you can write for particular elements. Few elements we will write now. Tell me one element. How can you tell, sir? Okay, I will tell myself. Oxygen. What's the atomic number for oxygen? 8. So 1s2, 2s2, 2p6. 8 electrons are there from lowest energy. We should follow all the 3 rules. What are they? Aufau principle, Pauli's Hunds rule, Pauli's exclusion principle, and then Hunds rule. Okay, right. So according to that, if you fail, it comes like this. But simultaneously, we can draw the cell diagram, orbital diagram also. For S, 2 electrons are there. P always 3 box, T always, D always 5, F always 7. Okay. 6 electron 1, 2, 3, 4, 5, 6. Okay. Right. So the same way. Tell me one more. Shall I? Yes. Neon. 1s2, 2s2, 2p6. 1 minute. I did mistake. Actually, this is the electronic configuration for neon because 2p4 because atomic number 8. 8 means 8 electron. 2 plus 2 4. 4 plus 4 8. So how do you fill the electron? 4 electron in there. P subcell 1 2 3 4. Okay. Now only we are going to write the electronic configuration for neon. One, two, three, 4, 5, 6. Okay. Yes. I hope you can write all the electronic configuration of at least first 10 elements. Please try to learn this very easy as well as important. Okay. Right. But here we are going to learn certain exceptionals. What are those exceptional we are going to learn? Chromium. What is the atomic number? Yes, 24. Then outer electronic configuration 4s2 3d4. Okay. Actually, our expected electronic configuration 4s2 3d4, but which existed 4s1 3d5. Why? It should have the half-filled electronic arrangement. So this is important. Later on, that means the very next topic, we will learn why they are trying to becoming half-filled or completely filled. Here you see D. D means 5 boxes, 5 subsets. 1 2 3 4 5. Okay, 1 2 3 4 5. Half filled nature. Half filled means more stable. Okay, completely filled as well as half filled orbitals are more stable. That's why that one of electron from the S is jumped over to the D orbital. It makes half filled electronic configuration. So as per the electronic configuration for chromium, you should write 4s1 3d5. I will write the complete one. 1s2, 2s2, 2p6, 3s2, 3p6, Next to that 4s1 3d 5. This is the electronic configuration. But as per the Hunds rule, sorry, alpha principle, 4s2 3d5 will come because lowest energy 4s. But here the half filled becoming more stable for chromium. That's why they are making themselves as a half filled orbital by shifting one electron from the 4s to 3d orbitals. Okay. Yes. The same way you have to remember for copper. What's the atomic number for copper? 29. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Actually expected 4s2, 3d9. Okay, but only one electron is becoming completely filled electronic configuration in the d orbital. That's why one of the electron from s is shifted and forming 4s1 3d10 completely filled, half filled, both becoming more stable orbitals. Okay, yes, now we can understood the orbital becoming S means S1 as well as S2. P means P3, P6. D means D5, D10. F means F7, 48 or more stable orbital formation. Why? These all are half filled, these all are fully filled or completely filled. Yes. The last, what is that? Stability of orbitals. How you learn about the stability of orbital? We can learn the stability of orbital, or we can determine by using the two terms. What are the two terms? Symmetry, and the another one is exchange energy. Okay, so now we will learn about symmetry. What do you mean symmetry? See, in the degenerate orbitals, all electron mutually or having equal number of electron means they are becoming more stable. Okay, other than not equally filled. Okay, for example, symmetry means we will see some example for actually it is also given for chromium, the last outer cell electron. What is that? 3d 5 4s2. Okay, so 4s2, sorry, 4s1, sorry, 4s1, that 4s1, only one electron we can leave it. Okay, what about that 3d5? See, 1 2 3 4. See, all 5 orientation of D. What is 5 orientation? Dx square y square, dz square, dxy, dyz, dzx. All the 5 orientations are having equally distributed, so it will have the equal shielding or equal repulsion. They will stable. But one of the orientation having the high electron, another having no electron means they may have the shielding. Okay, it may have the more repulsion. Okay, because of that, those who having half filled electronic configuration, they are more stable. Okay, let us talk about symmetry. Okay, for example, P3. How do you feel? All the three orbitals are singly filled, symmetric. All are equally distributed. D5. 1 2 3 4 5. F7. 3 4 5 6 7. The same way P6. All three orbitals are having equal number of electrons. 1 2 3 4 5 6 7 8 9 10. So if you see, all are equally distributed. Because of that they are more stable. Okay, right. Now we will learn about exchange energy. See, symmetry and exchange energy only makes the orbital becoming more stable. So symmetry we have finished the last one. exchange energy. What is exchange energy? Right? So in the degenerate orbital, very important, the same spin electron may exchange themselves. Very important. Degenerate orbital, so they are in the same energy level. Then same spin, that means clockwise rotating spin can exchange with another clockwise rotating electron. Okay, or both upward rotating or both downward can exchange. Okay, but other spin cannot exchange themselves. You note the point. Okay, so for that we can write the same chromium 3D file. Okay, how do you draw in the orbital diagram? 1, 2, 3, 4. Right? Each one having one electron. Okay. Now, what are the possibility for exchange? The first electron may shift toward or exchange with the second one, third one, fourth one, and then 5. Okay. So, how many possibilities? 1, 2, 3, 4. Then second electron, one, two, three, four. First electron leaving. Second electron may exchange with third one or the fourth one or fifth one. What about the first one? Already we have learned. Okay, 3 exchange possible. Okay. Third with fourth and as well as fifth. So the last one again we want to draw only the fourth one may exchange with the fifth one. So 1. 4 plus 3, 7. 7 plus 2, 9. 9 plus 1, 10. So how many exchange possible? 10 exchange possible. See, you just remember chromium acts as per the aufau principle. If you write 3d4 will come. If it is comes 4, only exchange possible 8. So here 10 exchange possible. So which one having more exchange, that becoming more stable. Okay. See, during this exchange what will happen? Some energy will release. Okay. That energy, releasing energy, only called exchange energy. Okay. Right. So by knowing the symmetry and exchange energy, we can say those who having half filled and they are having more exchange energy. Those who having half filled and completely filled, they are having symmetry. So those who having more symmetry as well as exchange energy, they are more stable. Okay, thank you.